Hello, this is Mr. Gilmore with the 7.2 Similar Polygons lesson. This entire chapter begins here with what we call similarity. The rest of our chapter will encounter what does similarity do and what are some theorems that are important to us that involve similarity. It even will carry us over into the next chapter, chapter 8, involving an important theorem that we see that uses similarity to prove that really important theorem. Let's talk about the rough idea of similarity first. When we think back to chapter 3 when we introduced the idea of congruence. When we say two figures are congruent, we say they have the same size and same shape. That's kind of the rough idea of congruence. But with similarity, we'll say that two figures are similar if they have the same shape. So it's not necessarily that they have the same size, but they will have the same shape. Now we want to actually define similarity a bit more precise. So what does really mean when we say two things are similar? Well, down below, if we take a look at these three colored triangles, I'm going to tell you that these three colored triangles are actually similar. When we talk about similarity, there's a couple of questions we can think of, like, what does it mean about the angles that correspond? So if I was talking about these angles here in the blue, the green, and the red, what could you say about those angles? Well, it appears that those angles are all equal. And that's actually true, that we're going to find that all of those angles here that correspond are equal. We can say the same thing about these angles here, that we're going to find those angles to be equal, and we're going to find that these angles here that correspond are all equal. Now, what about the sides? This is a bit of a harder question. What can we say about the sides that correspond? Well, as it turns out, we're going to learn that each of the sides, we use this fancy word that we actually learned about in our last lesson, proportional. So we're going to learn that the sides of these three triangles are actually going to be proportional to each other. So we take what we've learned here about our angles and about our sides, and we put them together into a precise definition. So the precise definition of similar polygons, here's what it says. Two polygons are similar if angles which correspond are equal and sides which correspond are proportional. So what does it really mean when I say sides are proportional? That means pick a pair of corresponding sides and make a ratio of them. Pick a second pair of corresponding sides, make another ratio of those. Those two ratios will be the same. They're going to be equal to each other. In other words, we can test it. The product of the means will equal the product of the extremes, just like we talked with our earlier about our proportions. So here's an example of two similar polygons. These two triangles, ABC and RST, are similar to each other. We can actually see we're given that all three corresponding angles are equal. In other words, A and R are equal, B and S are equal, C and T are equal, and our sides are proportional. In other words, if I make a ratio of two corresponding sides like AB and RS, 2.2 over 3.3, it's going to give me a number. That number is going to be the same for BC over ST and AC over RT. So what we actually have is what's called an extended proportion. We bring all three ratios together, set them all in equal to each other. Those sides are all going to give us the same value. Now, we have similarity statements, just like we have congruent statements. Similarity statements work just the same way, but we use a different symbol. We use the tilde to actually then write out the similarity between the two triangles or two polygons. So the statement triangle ABC then is similar to, that's how we're going to read that with the tilde in the middle of them, to triangle RST. So this says that triangle ABC and RST are similar. Notice that's really the top part of the congruent symbol. It's not the equal sign. We take that out of the congruent symbol, left with just the tilde on top. Now, just like with congruence, order matters in similarity, which means the first position must then correspond with the first position of our second polygon. So in other words, our example that we saw earlier, a triangle ABC is similar to triangle RST. That means A corresponds with R, B corresponds with S, and C corresponds with T. We can also then say which sides and angle, or which sides correspond. I can say that AB and RS correspond. I can set a ratio of them, because remember, in this case, we're not saying that the sides are going to be equal to each other. We're saying sides are proportional to each other. So we can use our similarity statement, even without a diagram, to match up corresponding parts and find out missing angle measures, or use that to find a missing side measure. So if I were to tell you triangle ABC is similar to triangle RST, then what I can do is match up my corresponding parts. So I'm telling you already that angle A is 30 degrees, angle S is 60 degrees, AB is 4 degrees, AB is 4, a length of 4, BC is 6, and RS is a length of 12. I want you to find these missing parts for me. Find missing part of angle B, the measure of angle C, angle R, and angle T, and then lastly find the measure of side ST. If you need to draw a diagram, it might help. So if I were to have a triangle here, triangle ABC, and a second triangle, triangle RST, I can match up corresponding parts. So I know A and R are in the same position, which means if A is 30 degrees, I know angle R is also going to be 30 degrees, which answers one of my questions. The measure of angle R equals 30 degrees. So that's one of them. Check. Let's take a look. I'm also given angle S is 60. Well, angle S corresponds with B, which means angle B is also 60 degrees. So I've got one of my second answers. The measure of angle B equals 60 degrees. There we go. Check. Now, using Tasty, since we know all three angles inside of a triangle add up to 180 degrees, I can then figure out what the measure of angle C and the measure of angle T are. They're both going to be 90 degrees. So with angle C and angle T, I can figure out both of those. The measure of angle C is going to equal the measure of angle T, which is both equal to 90 degrees. Now, the last one's a bit tricky. We want to find out what the measure of ST is. Well, the thing is, we know the sides of these two triangles are proportional. So we can set up a proportion between these sides and find the missing measure. So let's go ahead and fill in what we know. We know the length of AB is 4. We know the length of BC is 6. And we know the length of RS is 12. We can match up corresponding parts then. Let's take a look. 4 actually corresponds with 12, right? AB and RS correspond according to our statement, right, above, AB and RS. BC corresponds with ST. That's what we're looking for. Let's set a proportion. If I were to take the ratio of AB over RS, it would be the same ratio of BC over ST. Plug in the numbers. We have 4 over 12 is equal to 6 over ST. We can solve for ST. All right, so let's cross. Actually, I'm going to simplify this. 4/12 I can simplify to 1/3, right? And then I'm going to cross multiply. So I do 1 times ST is just ST. 3 times 6 is 18. And there we have it. Found our missing side for our triangle. So we can use proportions as well. That's why we've been setting up this idea of proportions to find missing side lengths within our triangles, or within our similar polygons. Let's do another example with similar polygons, solving for a value of x. So these two polygons below I'm going to tell you are similar. Now in this diagram you'll see that there's a single arc mark on some angles and a double arc mark on others. That means that those angles are actually going to be equal in measure to each other. So think of this angle C more like this to angle R and angle P and angle T, which means we can match up corresponding sides. As it turns out, our top side SB is going to be proportional to, or is corresponding to JH. So in other words, I'm going to set up proportions using these four sides and solve for a missing value of x. SB corresponds with JH, which means we have a ratio of 2 to 3, right? 2 over 3. And then I'm going to do from the smaller quadrilateral to the bigger quadrilateral, I have x plus 3 over 2x plus 2. And now I can then cross multiply and solve for x. So I'm going to make sure I distribute. I'm going to do the product of my extremes first. 2 times 2x is 4x. 2 times 2 is 4. I also distribute with my 3 in my means, so 3 times x is 3x, 3 times 3 is 9. Go ahead and solve for x. I'm going to subtract 3x on both sides. I get x plus 4 is equal to 9. Subtract 4 on both sides, I get x is equal to 5. And there we have it. So using that, the idea of similarity between these two polygons, we can set up proportional sides and solve for missing values. Now, let's move on to something called a scale factor. Let's go back to our assumption with our two triangles that triangle ABC is similar to triangle RST. This means, again, that I can set up an extended ratio or extended proportion between these three proportional sides of my triangles. So in other words, RS over AB is equal to ST over BC, which is equal to RT over AC. In other words, if I were to actually take RS divided by AB, it's going to give me a number. If I did the same thing for ST over BC, I get another number. And if I did RT over AC, I get another number. As it turns out, all three of those numbers I would get are equal to each other. They're all the same number. So in other words, let's let that number equal some sort of variable for us. Let's call that number K. Okay? I'm going to teach you that this K is actually called a scale factor. Let's learn what the scale factor means. So if I know that I have all three of those ratios equal to the same number K, let's actually set them all individually equal to K. So I know that RS over AB equals K, ST over BC equals K, and RT over AC equals K. Now with a little bit of algebra, right, multiplying both sides by the denominator of either AB, BC, and AC, I end up with the three equations down below. That RS is equal to K times AB, ST is equal to K times BC, and RT is equal to K times AC. This is now leading us into some sort of revelation about this value of K. As it turns out, what we have going for us is what we define to be a scale factor. When we say two polygons are similar, that means there is some value, some constant k, that we can take each side of one of the polygons and multiply it by that k value, and it turns into the side of its corresponding polygon. In other words, take a side, multiply it by its scale factor, it turns into the side of the other. We call that constant k the scale factor. So we actually can find the scale factor between two polygons by asking the question simply, what do we multiply one number by to turn it into the other? So here's a quick example. Let's find the scale factor between these two triangles, ABC and RST. In other words, I want to let's match up some corresponding sides. So 2.2 and 3.3 correspond. What number do I multiply 2.2 by to turn into 3.3? Whatever number that is, that's our scale factor. Think of this as an equation. I'm going to do 2.2 times some number, we'll call that number k, is equal to 3.3. Hey, that's an algebraic equation. One variable, one equation. I can solve for that variable. So I can divide both sides by 2.2. And as it turns out, 3.3 and 2.2 can actually simplify. 1.1 divides into each of them evenly. So 3.3 divided by 1.1 is just 3, and 2.2 divided by 1.1 is 2. So my scale factor is 3/2, 3 over 2. So take 2.2 and multiply it by 3/2, it's going to turn into 3.3. And what we've also done is we can say the same thing for the other pairs of sides. If I took 1.8 and multiplied it by 3 over 2, it's going to turn into 2.7. And the same story goes for our last pair of two sides. Now, did you notice something about that problem we just did? Not only were we looking for, when I asked you to find a scale factor, you had to choose a direction. Notice that I went from triangle ABC to triangle RST. Why did I do that? Well, I chose a direction, going from one triangle to the other. Could I have gone the other direction? The answer is yes. I could have actually gone from triangle RST back to triangle ABC. Let's actually do that. So now I want you to find another scale factor here, which is meaning take the values of RST, start with this side, 3.3, and multiply that number to turn it into 2.2. So now our equation changes a little bit. It looks like this. 3.3 times some number k is equal to 2.2. We can solve for k. As it turns out, when we do that, we get this number, 2/3. Now, what is the relationship then between the two scale factors we just found? If you notice that when we went from triangle ABC, so let me write this down. We went from triangle ABC to triangle RST, we got a scale factor of 3 over 2. Now compare that to this scale factor, 2 over 3. Notice what's similar about them? They are reciprocals of each other. So as it turns out, no matter which direction you pick, you know that the other direction scale factor is simply going to be the reciprocal of the one you just found. So if I started off with 3 over 2, then I know the reciprocal of my other direction is going to be 2 over 3. And that's the neat little pattern that we find within our scale factors. Now, the last little bit of information before we conclude this lesson is introducing the idea of a perimeter of a polygon. As it turns out, the perimeter of a polygon is also it's also proportional with the sides. In other words, if we make a ratio of the perimeters, it makes out the same ratio if we do with the individual pairs of sides. So just like RS over AB, ST over BC, RT over AC is the same as the perimeter of triangle RST over the perimeter of triangle ABC. In other words, we can actually set up proportions to solve for missing perimeters as well, even if we don't know what the individual side lengths are. So our last problem is an example using this new revelation of our perimeter ratios. So two similar polygons have a ratio of 3:2. The perimeter of the smaller polygon is 50. Find the perimeter of the larger polygon. Well, the perimeters have the same ratio as the sides, which means that the ratio of the two polygons is 3 over 2. That means we can set up a proportion to solve for the missing perimeter of our larger polygon. So our ratio is 3 over 2. Okay. Now, I have this perimeter of the smaller polygon given, which means I'm going to match it with my smaller number, my ratio. So that means 50 is going to go in the bottom. To find the perimeter of my larger polygon, that's going to go in the numerator of that fraction, of that ratio, because it's going to correspond with the larger value in our ratio. We simply then have a proportion that we can simply cross multiply and solve for p. So I'll multiply my means. 2 times p is 2p. I do the product of my extremes. 3 times 50 is 150. And then divide both sides by 2. I get the perimeter of my larger polygon is 75. So we can actually use this ratio in many different, or use the proportional sides of polygons many different ways. We can use similarity with individual sides, but we also use similarity with perimeters. So we've come to the end of our lesson 7.2 on introducing similarity between polygons. Recall that similar polygons have equal corresponding angles, but they have proportional corresponding sides. If you do have any questions on the 7.2 worksheet, please don't hesitate to email me and get back, or I'll get back with you. With that, be good and do good.